Have they done it? Has humanity finally crossed the threshold into one of the universe's greatest mysteries? Did the brilliant minds at CERN, the world's most advanced particle physics laboratory, actually succeed in creating a black hole right here on Earth? The very idea is both terrifying and fascinating, sparking imaginations and igniting debates across the globe. It conjures images of cosmic monsters, swirling darkness, and humanity meddling with powers far beyond our comprehension, almost like something out of a science fiction movie. But let's set the record straight. The simple answer is no. Scientists have not created a black hole at CERN, or anywhere else on our planet. The rumors, the viral social media posts, and the dramatic headlines you may have seen are products of imagination, not reality. They're fueled by misunderstanding and a dash of sensationalism. The Large Hadron Collider is indeed the most powerful particle accelerator ever built, but it's nowhere near capable of forging a genuine black hole like those found in deep space. The energy required to create even the tiniest black hole is far beyond anything we can generate with current technology, millions of times greater than what the LHC can achieve. This persistent story comes from misunderstandings about what scientists are actually doing at CERN and how particle collisions work. CERN's experiments probe the universe's building blocks, sometimes exploring exotic concepts like microscopic black holes, but only as theoretical possibilities, not as real, dangerous objects. The truth is far more subtle and profound than the myth. It's a story of human curiosity, of pushing the boundaries of knowledge, not of impending doom or reckless experimentation. Every step at CERN is grounded in decades of research, rigorous safety assessments, and international collaboration. Thousands of scientists from around the world work together, ensuring that every experiment is as safe as it is groundbreaking. To understand the black hole myth, we first need to know what CERN actually is and why it captures the imagination of so many people around the world. CERN is home to the Large Hadron Collider, or LHC, which is the largest and most powerful scientific instrument ever constructed by humanity. It's a place where thousands of scientists from over 100 countries come together to unlock the secrets of the universe. Imagine a 27-kilometer ring-shaped tunnel buried 100 meters beneath the ground, stretching beneath the border of Switzerland and France. Inside, two beams of protons are accelerated in opposite directions to nearly the speed of light, guided by powerful superconducting magnets. These beams are then smashed together in head-on collisions, recreating the extreme conditions that existed just a fraction of a second after the Big Bang, when the universe was unimaginably hot and dense. By studying the debris from these collisions, scientists can glimpse particles and forces that haven't existed freely since the universe's earliest moments, offering a window into the birth of everything we know. In a sense, the LHC acts like a time machine, allowing us to look back 13.8 billion years and explore the fundamental building blocks of reality itself. Its purpose is driven by pure curiosity, to answer the most profound questions about what the universe is made of and how it all began. The standard model of particle physics is our best theory so far, but it's incomplete. It can't explain gravity, the mysterious dark matter that holds galaxies together, or the dark energy that's causing the universe to expand faster and faster. By smashing particles together at unprecedented energies, the LHC helps us search for cracks in our current theories and opens the door to discovering entirely new physics, perhaps even new dimensions or unknown particles. Every single collision is recorded by enormous, state-of-the-art detectors, and teams of scientists around the globe sift through mountains of data, searching for the tiniest hints of something new. It's a painstaking, collaborative effort that requires patience, creativity, and teamwork to answer the universe's biggest and most challenging questions. The LHC is not a weapon or a hazard. It's a tool for discovery, designed to expand our understanding of the cosmos and push the boundaries of human knowledge. So what is a black hole? In simple terms, it's a region where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse, leaving behind a warped region of space-time. The event horizon is the point of no return. Cross it, and you're lost to the singularity. Black holes fascinate us because they push physics to its limits, where our theories break down. The idea of creating one in a lab comes from theories like string theory, which suggest extra dimensions could make gravity stronger at small scales. In that scenario, high-energy collisions might create microscopic black holes, but these would be subatomic, with the mass of a few thousand protons, and incredibly unstable. According to Hawking radiation, such black holes would evaporate almost instantly. A microscopic black hole at the LHC would vanish in less than a trillionth of a second. There's no danger, just a fleeting, fascinating phenomenon. The fear of CERN creating a world-eating black hole is pure science fiction. Despite the dramatic headlines and viral internet rumors, there is no scientific basis for these concerns. The idea has captured the public imagination, but it's important to separate fact from fantasy. The myth goes like this. A tiny black hole forms inside the Large Hadron Collider, falls to Earth's core, and devours the planet from the inside out. It sounds like the plot of a blockbuster movie, but it simply doesn't hold up to scientific scrutiny. In reality, any black hole the LHC could possibly create would evaporate instantly due to a phenomenon called Hawking radiation. This process, predicted by Stephen Hawking, means that such black holes lose mass and energy almost immediately after forming. Its lifespan would be unimaginably short, gone in a fraction of a second, long before it could interact with anything around it. There's simply no time for it to cause any harm. Even if, against all odds, it were somehow stable, its gravity would be so weak that it would pass through Earth without leaving a trace. It wouldn't be able to pull in matter or grow larger. The Earth is mostly empty space at the atomic level. The odds of a black hole actually hitting and interacting with anything are astronomically low, virtually zero. Scientists have rigorously reviewed the risks, running countless calculations and simulations. Multiple independent safety assessments, conducted by experts from around the world, have found no credible threat from the LHC's experiments. The myth persists because stories are powerful and fear is contagious. But the laws of physics are clear and unyielding. Science is built on evidence, not speculation. The LHC is not a reckless gamble. It's a carefully controlled experiment, monitored by some of the brightest minds in the world. Every step is taken with safety as the top priority. The real risk is non-existent, and the science is sound. The evidence overwhelmingly supports the safety of these experiments. The doomsday scenario is just a story, not a scientific reality. It's a myth that belongs in fiction, not in our understanding of science. CERN's work is about discovery, not danger. By pushing the boundaries of knowledge, scientists at CERN are helping us better understand the universe, not threatening its existence. The strongest safety argument comes from nature itself. For billions of years, Earth has been bombarded by cosmic rays, particles with energies far higher than the LHC can produce. These collisions happen constantly in our atmosphere, yet the planet remains intact. If dangerous black holes could form this way, Earth would have vanished long ago. The universe is the ultimate safety test, and it's passed. CERN's experiments simply recreate, in a controlled way, what nature does all the time. The continued existence of Earth and other planets is proof that collider-made black holes are not a threat. The fear is unfounded. Nature has already run the experiment safely for eons. In 2025, headlines screamed about a black hole bomb in a lab. The reality? Scientists built a safe, clever analog to test a 50-year-old theory, not a real black hole. Inspired by Roger Penrose's idea, they used a spinning cylinder and magnetic fields to mimic how energy could be extracted from a rotating black hole. The experiment showed waves could draw energy from the cylinder's rotation, confirming Penrose's prediction. This was the first time the effect was seen in a physical system. It's a triumph of experimental physics, not a cosmic threat. Scientists often build analogs using water or sound waves to study black hole physics safely. The black hole bomb is a beautiful demonstration of fundamental principles, not a weapon. It proves our understanding of black hole physics is on the right track. Science advances by clever experiments, not by courting disaster. Black hole research isn't just in colliders, it's happening in quantum computers too. Recently, scientists used a quantum computer to simulate a baby wormhole. This wasn't a real tunnel through space-time, but a mathematical simulation based on quantum equations. Wormholes, in theory, are shortcuts through space-time, but real ones are likely unstable. The simulation explored the link between quantum entanglement and wormholes, a cutting-edge idea in physics. Researchers sent information through the simulation, and it behaved as if it passed through a tiny wormhole. This achievement shows quantum computers can help us study the deep connections between gravity and quantum mechanics. It's a virtual lab for probing the universe's most mysterious phenomena. Black holes are a playground for science fiction, inspiring stories of cosmic power and danger. Recent comics imagine scientists creating and containing black holes with quantum fields, a thrilling idea, but pure fiction. In reality, quantum entanglement can't stabilize a black hole. It's not a force field. Science fiction asks, what if? And inspires us, but real science demands evidence and consistency. Theories about micro-black holes at the LHC also predict their instant evaporation. You can't cherry-pick the dramatic parts and ignore the science. Science fiction and real science both have value. One inspires, the other discovers. The real-world experiments, like the black hole bomb analog and wormhole simulation, are just as profound as any story. Human ingenuity turns imagination into knowledge, safely and cleverly. The line between fiction and reality is clear, but both push us to explore. If we're not making real black holes, why study them? Because they're the universe's ultimate laboratories. Black holes push the laws of nature to their limits, holding clues to unifying gravity and quantum mechanics. At a black hole's event horizon, our best theories break down, showing our understanding is incomplete. We need a theory of quantum gravity, and black holes are the key to finding it. By studying them, even through analogs and simulations, we gather clues for this deeper theory. The mysteries are profound. What happens to information in a black hole? What is the true nature of the singularity? These questions drive scientists worldwide. Research at CERN and beyond is about exploration, not risk. The quest to understand black holes is a quest to understand everything, and it's a journey worth taking.